before I go, any questions on this? Mitch? Now, back up. We have very little of this on the homework. We have a couple of difference equations. You've done a little bit on 7A, and I think an 8A, something like that. You've seen one little block diagram on 8A, so look at a couple of these, okay? Hint, hint. Look at a couple of these, okay? On old exams. All right, Mitch, go ahead.
Did?
Pardon?
The one you just did?
Like what you just did, yeah. That sort of stuff. Because it really isn't very hard. So don't be losing points on something that isn't hard just because you didn't look at it. You could say, wait a minute, we never really did that in class. But you know what? It's on the homework. So. All right. It just isn't terribly, there's not that much of it on the homework. Spring 13, did you say?
16.
16.
It's the Nyquist one on question 7.
Good one.
Spring 16, problem 7. This is weird. I'm missing this number again.
Oh yeah, that's a good one.
Think that I could number things in order. Which problem are we looking at?
7.
Oh, I'm looking at 17, spring 17. No wonder I'm not finding it.
Do you want this one?
Spring 16, number 7. Yeah. Okay, it's closed book 7, right?
Yes.
All right, there we go. Good. Let me erase this. You got too many energy drinks?
Living off of them, huh?
Well, that's funny because you don't look particularly energetic.
Yeah. It's true.
How about trying the old-fashioned way of getting some sleep?
What's that?
What's that?
What is that?
It's what you got when you were in high school on the weekends.
Oh.
It's called a high school weekend thing. Let's see. It's 1.6 crosses there. This is spring 16, closed book 7. Let's see what is this. And this crosses here at 0.7, so we're not very accurate in the drawing. Let's see. There's a couple of other things shown here. This crosses here when omega is equal to 4, and it is at negative 4j. This crosses, let's see, there are some dotted lines here. 1.4j, negative 1.4. Isn't this one of your homework assignments?
Probably familiar.
Yeah, it's pretty close to that.
All right, so there's a little bit of extra information given here that is not on a regular Nyquist plot. There's some frequency information given at some points.
Yeah.
All parts of this problem refer to the system whose Nyquist curve is shown at right. Only the portion for omega greater than 0 is shown or plotted. Recall that the Nyquist curve represents the frequency response of the open loop system. If g of s is the open loop transfer function, let's see, the open loop transfer function is closed loop transfer function is g of s over 1 plus g of s. The open loop system is stable. Show the work for each part. When I say the open loop system is stable, what does that tell you?
P.
Z0.
That's what that piece of information is giving you. When I say the open loop system is stable, P is equal to 0. This open loop system has no poles in the right half plane or on the j-omega axis. Is the closed loop system stable? Well, we have to find what point. -1 here. And -1, we would take a line through here and we'd say that is an encirclement and that is an encirclement. And the way I find my direction is this starts where omega equals 0. We're going in this direction as omega increases. So what are the number of encirclements right there?
2.
2. Yeah. So in that case, Z equals N plus P equals 2 plus 0 equals 2. Pretty complicated math.
Very.
How many unstable poles? So is the closed loop system stable? A?
Yeah.
No. How many unstable poles does the closed loop system have?
2.
2. Good. Give the steady state response ys of t, steady state of t, of the open loop system to an input at x of t equals 5 cosine 7t. So x of t equals 5 cosine 7t. What we're doing here is almost exactly the same thing as we just did here. And this stuff right here. Only thing is we have a different plot. So is there a place on this plot where omega is equal to 7?
Yeah.
Yeah, it's right here. So given these dotted lines that say 1.4, -1.4, and -1.4j, can you tell what the magnitude and angle is of the transfer function at that point?
Yes.
In fact, you can say that P of J7 is equal to -1.4, -1.4j. It's actually equal to that. Literally equal to that, which means it has a magnitude and a phase. What's 1.4 squared, plus 1.4 squared square root? 2. Roughly 2. 2 at what angle?
45.
45.
Negative 135 degrees. And you don't have to look at this, you just have to look at this angle right here. Negative 135 degrees. So that's our transfer function. We need to change this into a phasor. What is the phasor representation of 5 cosine 17?
5 angle 0.
0.
5 angle 0. So if I'm looking for the open loop response to this system, what am I doing? So once again, it's a question of, do you know what that plot is telling you? Now, the real truth of the matter is that figuring out what omega is along the plot is usually very difficult from just the plot. So, but the fact that it's given to you for some positions is helpful. Yeah.
When you're trying to do closed loop, you take the P of J7 over 1 plus P J7.
Yes.
That's okay.
And I think that's the next question, only it's probably about 4, not 7, since 4 is given up there.
Part F.
Yeah, okay. Part F. No, that's 8. So what if we were given, what if we were now asked, so this is open loop response to this input. What if we were asked for the closed loop response to, let's say, 3 cosine of 4t. We aren't in this particular problem, but what if we were? What would we do now?
He's now going to be 4 equal negative 90 degrees.
P of J4 is equal to 4 angle negative 90 degrees or negative 4J, either way. If we need to have the closed loop response, we need to figure out what P of 4J over 1 plus P of 4J is, in which case we would need probably do this, 4 at negative 90 on top, and the bottom do 1 minus 4J. Why do I write it in the 2 different forms?
You can find the angle to the bottom, you can just subtract.
Yeah, because I gotta add it to 1. So it's just a whole lot easier on the bottom to have it in that form. So I end up with 4 over 1 plus 16 square root. What did I do there? At an angle of inverse tangent of negative 4 over 1. And I can figure out a magnitude and an angle out of that. Once I have a magnitude and an angle, what do I do with this? What is this expressed in phasor form?
3 equals 0.
3 angle 0, so I multiply by 3 angle 0. Does that help there? Yes?
So by you tacking on the closed loop response part to this question, I'm assuming that on the test you're likely to have an open loop response and a closed loop response part of the question.
Yeah, you have seen that a couple of times. You've seen it in, especially with the Bode plots.
Right.
So to be honest, it's more likely to show up with the Bode plot than with the Nyquist plot.
Okay.
Although you did have a problem, I think, very, very similar to this with both an open loop and a closed loop with an Nyquist plot. So, yeah, it could be. So now, the next part is the gain is reduced by a factor of 2, that is multiplied by 0.5. And that's going to be the case for the rest of the problem. If I do that, one way to look at that is I shrink this. Another way to look at that is this is now what? 3. This is now what? This is now what? This is now what? This is now, let's see. This is now negative 2j. Anything else have to change? So where is negative 1 now? So it's easier to think of the axes as shrinking than the thing as expanding. Because that thing expanding is a real pain in the neck. All right, so I've done that. Now, what are the encirclements? I think you can tell without even drawing a line.
Sure.
Is the system now stable? The closed loop system. Yeah. What is the phase margin of the closed loop system?
45 degrees.
How the heck did you get that?
Well, now that point that was at around 2 is now 1.
Yeah, because this distance, because of the numbers I chose, or not 0.1, but about 1.
Oh, I see.
So that's where the unit circle crosses. A little bit tricky there.
It is.
But that's where the closed loop system. So I use numbers like 0.7, 0.7. Or I use numbers like 0.6 and 0.8. Things that are pretty obvious that comes to up to 1. And if it was doubled beforehand, you know, and I can play with those, but look for something that gives that.